Thank you for the introduction. Thank you also for the invitation, for giving me the opportunity to give this talk on our polynomial and application to coding theory. Let's start. So I first would like to introduce what are our polynomials. So this, can you see? No. Really? So it's setting in blue. It's better in black. Okay.
Stay away from blue.
Try.
Turn the light down.
Yeah, so what is a... No. Oh. It's okay. Hope so? Okay. So I will write just copy the notation in the blackboard. So K is a field. So the setting is the following. So K is a field. I consider a morphism of ring from K to K, which I call phi or phi. The morphism of ring. And then I consider D from K to K, which is what we call a phi derivation. So what is, by definition, a phi derivation? It's an application from K to K, which is additive and satisfies this twisted Leibniz rule. So D of AB equals phi of A times D of B plus D of A times B. So it's what we call a phi derivation, and you see that if phi is the identity, then this condition is just the usual Leibniz rule. D of AB equals A times D of B plus D of A times B. Okay, and now I can define the OA ring, which I denote by K of X, phi, and D. So it's a non-commutative ring in general. It is described as follows. So first I describe its elements. So elements are just usual univariate polynomials over K. So I insist that are univariate polynomials. So the variable is this X, and this phi and this D just some extra, in the notation, some just extra letters for denoting the twisting isomorphism, they are not variables. Then the addition is also very natural. It's a standard addition, but the multiplication is a bit different than the usual multiplication. It is twisted by this rule. If you have the variable x multiplied by a scalar on the right, a, then it's given by this expression, which is phi of a times x plus d of a. So we have something which is twisted. Okay, so this is a definition of array polynomials, and let me show you some example of computation. So I will call you the rule here, and let me show you how we can compute x squared times a. So you just write that it's x times xa, right? And now you use a commutation relation to say that xa is phi of a times x plus d of a. You expand everything, you get this expression. Then this x times phi of a, you can just reuse this rule with x replaced by phi of a in order to get an expression of this. And you get this. X times d of a is something like that. It's not that important what are the results. And then you refactor everything, and you get this expression for x squared times a. So I think I have convinced you that we can compute in the same way x cubed times a and x4 times a and so on and so forth. And so we have an expression for x to the n times a for any integer n. Okay. And now if we want to compute the product of two OA polynomials, for instance, two OA polynomials of degree 2, like this, then you just expand everything without permitting any x and a, b, c, d. You get this expression. And now x to the 4, is x to the 4. And the second summand, x to the square times cx, you can rewrite it using the expression of x to the square times c. You get from here. And you get this expression. And so on and you continue for the other summands. Don't want to be complete because the result is quite long. But you get, so this computation is here because I would like to, I wanted to convince you that this rule I used to define the multiplication really defines the multiplication in this ring of polynomials. Okay. And here another example. So if you are working over the complex number C, and you choose for the twisting isomorphism the conjugacy, x maps to the conjugate of z maps to the conjugate of z. And if you are just taking 0 for the derivation, so in what follows I will often you take d equals 0, and so I will omit it in the notation. So in this particular ring, then you have this computation, for instance, which is a remarkable identity. So x plus a times x minus the conjugate of a is x squared times the norm of a square. Okay, so you can check this just by expanding the left-hand side. And as a consequence, you see that our polynomials actually can admit many factorization. For instance, the polynomial x squared minus 1 in this ring as factors as x plus a times x minus a conjugate for all a of norm 1. So we have infinitely many factorization for one polynomial. So it's a bit different from standard polynomials. But in any case, our polynomials look like usual polynomials for several. They share several features with usual polynomials. For instance, the first thing is that we have a well-notion of degree, a well-defined notion of degree on OA polynomials. That is a usual standard degree, and this degree behaves as we expect. So if you have two OA polynomials f and g, then the degree of the sum is at most the maximum of the degree of the summands, and the degree of the product is the sum of the degree of the terms, as you can imagine. Maybe something which is not so a little bit more unexpected is that this ring of OA polynomials admits is right Euclidean. It admits right Euclidean division. So it's just this. If you have a and b, two OA polynomials with b non-zero, then you can just write a equals qb plus r for q and r two OA polynomials, which are uniquely determined with this condition and the fact that the degree of the remainder is at most strictly less than the degree of the divisor. So standard fact, except that you have to be careful that you really have to write a equals qb plus r and not a equals bq plus r, otherwise it's false. Anyway. The corollary is that this ring of OA polynomials, k of x phi d, is left principal, meaning that all left ideal are principal generated by one element, and you have a notion of right GCD and left LCM. So you have to be careful between left and right, but okay. So this property has really, you can continue this list. For instance, there is the usual Euclidean algorithm makes sense in this non-commutative context, and so on and so on. Okay, so these are the OA polynomials, and I will of course come back on this, but this is a very standard property of them. I will just want to present in the very short first part of my talk. And maybe you are you are wondering why we are interested in these polynomials. So I will, in the rest of my talk, I will explain some application to coding theory of this setting. But this polynomial were first introduced by Ore in the 30s, I think, if I remember correctly. And the motivation was not coding theory at that time. It just want to because it's a very standard construction in non-commutative algebra. It really helps. It's really the first example, maybe not the first, but one of the first examples of non-commutative algebra and non-commutative rings. And it's just like polynomials are useful for studying rings, or polynomials are really useful for studying non-commutative rings, non-commutating ring theory. It's a very central object. And it's also very useful for studying semi-linear algebra and linear differential equations. So for instance, if phi is the identity, then the ring of Ore polynomials are nothing but the ring of linear differential operators. And so it's very useful for studying linear differential equations. And if D is 0, then it is related to semi-linear algebra, just like usual polynomials are related to linear algebra. So you have the characteristic polynomial, factorization polynomial, polynomial of endomorphism, and so on. And if you are not interested in linear algebra but semi-linear algebra for some reason, then the natural setting is this, Ore polynomials. Okay, but it's not what I want to discuss in this talk. What I want to discuss is application to coding theory, because there is some. And so before, I probably need to recall you some basics of coding theories, although probably you all know what will be on this slide. Anyway, so first of all, the definition of a linear code. So K is still a field. We give a field as before. And so a linear code is a subspace, K linear subspace of K to the n for some integer n. Okay. So this integer n is called the length of the code. The dimension of the vector space is called the dimension of the code, without any surprise. And another important notion on linear code is the minimal distance. So the minimal distance of a code is the minimal of W of x for any x in C who is not 0. So the elements in C are usually called the code words. So I will probably use this terminology in what follows, but I'm sure I will try to avoid it. And W of x is what we call the Hamming weight. And the Hamming weight, by definition, of a vector, so x is an element of K to the n, so x1, x2, xn, is a number of non-zero coordinates of x. So this defines a distance on K to the n. So the distance between x and y is a weight of the difference, x minus 1, and so it's also the number of coordinates on which x and y differ. So here is a beautiful example of linear code. So you can see, I hope, it's not so important to see this number here, but there are 7, each word has 7 bits, so it's a natural subspace of f2 to the 7. So it's a linear code over f2 of length 7, sorry. It has dimension 3, because there are 1, 2, 3, 4, 5, 6, 7, 8 elements. And you can see that it's a linear subspace. You can check that it's indeed a linear subspace. And it has a minimal distance 4, I think, because each non-zero element of this code has 4, 1, and 3, 0. So the minimal, actually it's even better. The weight of any non-zero element is 4, and so the minimal is also 4, of course. But okay, and we have a theorem, a well-known theorem, which is called the Singleton Bound, saying that if you have any linear code, then there is a relation between an inequality between the distance, the dimension, and the length. What is the minimal distance plus the dimension is always at most the length plus 1. So it's really easy to prove this theorem, this bound. And we might be interested in those codes for which this bound is actually an equality, and they are called, in general, MDS code for maximal distance separable codes. Okay. So now I want to give you, a very classical construction of codes, which are Reed-Solomon codes, which is very important for theory, in the theory. So the setting is the following. We have k and n, two positive integers with k less than n, or equal, but in general k will be less than n. We are just considering A1, A2, A3, and so on until AN, pairwise distinct elements of K. So it implies in particular that N is less than or equal the cardinality of K. So if you're working over finite fields, then this gives some restriction. And what is the associated with Solomon code is, I will denote it by Reed-Solomon of K and Y and 2 and so on. It's an image of this mapping. So you take K of X is a ring of polynomial ring over K, usual polynomial ring, not twisted. This subscript less than K means that I'm considering all the polynomials of degree less than K, strictly less than K. And when I have such a polynomial, I can evaluate it at A1, A2, A3, and so on. And I get this way a tuple of n elements in K. And the code is by definition all the tuple I can obtain this way for from a polynomial of degree less than K. Right? So of course, if K is n, then this map is a bijection. But if K is less than n, in general, it's only injective, and so I get a strict subspace of K to the n, which is called the Reed-Solomon code. And the theorem is that we know the parameters of this code. So of course, the length is n by definition. It's not difficult to compute. The dimension is K because this map is injective. And the minimal distance is n minus K plus 1. It's just it follows from the fact that a polynomial of degree at most k minus 1 has at most k minus 1, 0. And so you see that in that particular case, Singleton Bound is reached, right? So it's an example of maximum distance separable code. So these codes are interesting for this reason, but are also interesting because they allow for an efficient decoding algorithm. So I don't want to speak about decoding in that talk, so I will skip this, but there are important codes in the literature. Okay, so that's for Reed-Solomon codes, and now I want to define what are Gabidulin codes, and I will just show you that it's almost the same. I mean, it's a bit different, but it's the same spirit. So instead of taking a pairwise distinct element in K, I'm taking a linearly independent element of K. So linearly independent over Fp, and now I have to assume that K is a finite field Fq. So in that case, the associated Gabidulin code, which is now denoted by Gab of K and A1, AN, is the image of almost the same map, except that I'm not considering all polynomial, but what we call linearized polynomial, and of height. In general, we say height instead of degree now, strictly less than K. And what is a linearized polynomial? It's something like this. It's just a polynomial with a term in x to the p, x to the p square, x to the p cube, and so on, until x to the p to the k minus 1. So they are called linearized because mapping x maps to x maps to x to the p, and so on are Fp linear. And so this is almost the same, except that instead of evaluating polynomials of degree less than k, we are evaluating linearized polynomial of height less than k. Otherwise, exactly the same. And the point is that we have exactly the same theorem. The length, of course, is n, the dimension is still k, and the minimal distance is still L minus k plus 1. So there are also maximum distance separable codes. And it's even better than case, because the minimal distance is n plus k minus 1, but for the Hamming distance I've defined earlier, but also for another distance, which is finer in some sense, which is called the rank distance. And what is the rank distance? It's a kind of linearized version of Hamming distance. So instead of counting the number of coordinates of x which are non-zero, we consider the span of all the coordinates of x, and we count the dimension of the span over fp. So if you have, for instance, if you have the vector 1, 1, 1, 1, 1, then the dimension of the span is 1, even if the coordinates are all different from 0. And so this rank distance is less than the Hamming distance, is not greater than the Hamming distance, because it's rather clear. And so having a minimal distance, having the maximal possible minimal distance for the rank distance is better than, it's better than having the maximal minimal distance for the Hamming distance. So it's even better for this. Okay, so let me. So these codes were, so they are called Gabidulin codes, but actually they were first defined by Delsarte, and then rediscovered some years later by Roth, and then rediscovered a second time by Gabidulin. But they are nowadays called Gabidulin codes. So first of all, they were described in these terms, but now we prefer another way of thinking at them. Okay. So you see, I have this linearized polynomial, but the map, of course, the map x maps to x to the p is the Frobenius. X maps to x to the p square is the square of the Frobenius. So in fact, I'm evaluating a polynomial in the Frobenius in a1, a2, an. So instead of writing, so maybe it's not so. Instead of writing f of a1, f of a2, f of an, I prefer. I can just say that I'm evaluating a polynomial. I'm evaluating the polynomial f at the Frobenius, and then apply it to a1. Apply the map I get to a1 an. So now I no longer have a linearized polynomial, but just a standard polynomial, except that it's a polynomial in the Frobenius, and the point is that the Frobenius does not commute with scalars. If you apply the Frobenius and then. If you multiply by a scalar and then apply the Frobenius, it's the same that applying the Frobenius, but multiplying by the scalar to the power p, because of linearity. And so you have this commutation relation between the variable x and the scalars. X times a in this ring of polynomial is a to the p times x, and so it's exactly the the domain is a OA ring and not a standard ring of polynomials. Okay, so we can just make further simplifications. Instead of evaluating f of phi at a1, a2, and so on, we can just give the f of phi, the linear mapping. So f of phi is a linear mapping, so given it at, I think that's it, yeah. So I mean that I'm just mapping f of x to f of phi restricted to some subspace V, where V is a subspace generated by a1, a2, and an. Right? So now the image is not k to the n, but it's a set of homomorphism from V to k. And so instead of, and the rank distance now is a bit different. And so we don't have to compute the rank distance of some vector in k to the n, but of some homomorphism from V to k. So the rank distance of U here is actually, if you try to figure out what is this, is the span of the dimension of the span of the rows or the column of some matrix, and that's the rank of the matrix. So it's a reason it's called the rank distance. Okay. And remember that A1, A2 up to AN, I just forgot it and replaced by the span of this. So instead of the data, the initial data is no longer A1, AN, but a vector space V, which is should be here, a sub-vector space of k to the n, and the Gabidulin cone I will denote just by Gabidulin of k and v. So let me maybe just read this once again. So I consider V a sub-fp vector space of some fq, and then the associated Gabidulin code, which is denoted by Gabidulin of k and v, is the image of this mapping array polynomial to this array polynomial evaluated at the Frobenius, restricted to v. If you don't want to restrict it, even can do also. Can take v equals k, it's a perfect choice. Yeah, so what do we care about the rank distance? So of course we can say that it's a very beautiful mathematical construction, but in fact array polynomials, the Gabidulin code were defined maybe 50 years ago, and indeed they were more or less forgotten, not exactly, but not such work has been done on it for some time, and nowadays there is much more attention on them, so because there are practical applications. So there are a few of them, but the most standard one is application to what we call network coding. So network coding is this problematic. We have many computers distributed all over the world. And this computer, which is a server, say, and this one also, has a message A, and this one has a message B. And this computer wants to transmit this message A to the computer here, below, and to this one. So two on the bottom. And the same for this computer, this server. So the message A should arrive here and there, and the message B should arrive here and there as well. So what we can do, of course, is something like this. For instance, you let the message A transmit go to this pipe, and the message A go to this through this path, for instance, and the same for the message B. But you say that on this solution, this pipe is used 2 times, and so it's not so good for the bandwidth. And you can just try to figure out what can be done, but in any case, you have to use a pipe 2 times. But you can think at another solution, which is the following. So I transmit A here and there, and B here and there, and so this computer has A, this computer receives A, this one receives B, and this one receives A and B. And instead of transmitting A and B separately, you can just compute the sum of A and B. Say A and B are elements in some field. I don't know. It's not so important. You can just view them as elements in any vector space. And so he computes A plus B and transmits the sum A plus B. And then this one transmits A plus B on the left and then plus B on the right. And so it means that this computer has received A and A plus B. And so you can just, by making the difference, reconstruct B. And the same on the right, sorry. And so with this solution, we see that we are managed to transmit A and B to the both. We managed to transmit A and B to the both computer as we wanted to, using only each pipe 1 time. So it's a solution which is more and more used in practice for network transmission, and you see that the theory of natural Hamming distance as a classical coding theory is not really relevant in that case, because what we want to do, the problem we have to face is, for instance, if at some point some server is down, or is infected by the virus, or is, I don't know, there is some problem with some server, and in that case, the whole message is corrupted. And so classical coding theory is not relevant, but coding theory with respect to the long distance becomes relevant because if if for instance this message is altered, then it will eventually it will give an error of rank 1. And if two computers are I don't know, are infested or something, are down, or I don't know, then the resulting error will have rank 2 and so on. And so, because we are making all linear transformations. And so it's a way to prevent to prevent communication in this model. So it's a reason why Gabidulin codes are important nowadays. Anyway, you. Okay, so there is still another. No, okay. So there is still another generalization of Gabidulin codes that I would like to present now, which is more recent. And for this, I need to introduce more evaluation morphisms. So I have new assumptions. So from now on, I will assume that K is a field equipped with phi as before, but K is no longer needs no longer to be a finite field. It can be any field. And I introduce this subfield F, which is a field of elements fixed by K. So F is a set of a subfield of K consisting of elements such that phi of x equals x. Right? And I assume that K over F is finite. It's a finite extension, so it's a Galois extension. Cyclic Galois extension with Galois group is generated by phi. In particular, it implies that phi has finite order. It's bijective. So as I said in the definition of Gabidulin codes, we have encountered this evaluation morphism mapping f of x to f of phi. And the fact that we are working with array polynomials on the left ensures that this evaluation morphism is actually a homomorphism of rings. It's commute with a multiplication. But actually, more generally, if we have any semilinear mapping from V to V, where V is a K vector space, so semilinear mapping is something which is additive and satisfies this axiom. So alpha of x equals phi of x times alpha of phi of a times alpha of x. So it's like linear mapping, except that we have to twist the scalar by twisting morphism. So in that case, we have also a well-defined evaluation morphism consisting in mapping an array polynomial f of x to f of alpha. Yeah.
Should be gm of k or homomorphism of k?
Sorry?
Here the evaluation should be the morphism of gm of k or just k?
The morphism of evaluation? And the morphism of k. So I don't understand your question.
I thought that this is for Venus, okay.
That's fine?
No.
Okay. So you can evaluate not only at phi, but at any alpha, which is a semilinear mapping acting on some K vector space. And the proposition is that it's a classification proposition. It's rather straightforward to prove this proposition, but the semilinear mapping of K from K to K are just the multiplier of phi. A times phi for some A in K. And so using this, you see what you can do. Instead of evaluating only at phi, we can just evaluate at other alpha of this form and get this way a more general Gabidulin codes. So it's what we call the linearized Gabidulin codes, which were defined by Martinez-Penas recently. And also by, in a different spirit, with different notation by Delphine Boucher, but I will use the presentation of Martinez-Penas, which is more suitable for what I wanted to say here today. So I consider, as before, k and m two integers, and a1, am elements of non-zero elements of k, and I assume that the norm of the ai, the norm of k over a, are pairwise distinct, so now the right condition. And I'm considering also v1, v2, vm sub f vector spaces of k, so that plays the role of the v as the previous slide. And then the linearized Reed-Solomon code associated to this data, which is denoted by LRS, linearized Reed-Solomon, of k, a1, v1, a2, v2, am, vm. It's the image of this mapping. So you take some OA polynomial and you evaluate it at a1 phi, a2 phi, am phi. Okay, so it's something which makes the Gabidulin construction and the Reed-Solomon construction. So now OA polynomials, the natural points for evaluating OA polynomials are these semilinear mappings. And I consider many semilinear mappings, A1 phi, and A1 phi, A2 phi, and so on. And I evaluate the OA polynomials at these points. Okay? And theorem is almost the same as before, is that the length of this code is, so it's the computation is a bit, the computation is so we have to compute the dimension over k of the codomain of this map, which is the dimension of v1 plus the dimension of v2 plus the dimension of vm.
What's the image of this map? K in k?
Sorry?
So you're saying it's a homomorphism from v1 to k.
Yeah.
Why is the image in k? Why did they? Because they.
Yes, because A1 phi is a mapping from k to k.
Okay.
So the length is this. Yeah. So we can imagine that we are considering more general semilinear morphism, and yeah, but I'm just sticking to this. So the length is n, the dimension is k, and again the minimal distance is n minus k plus 1. So say it's a minimal distance for the Hamming distance, but actually it's a minimum distance for a refined distance as before, which is called the sum rank distance. You have elements u1, um. ui lies is a morphism from vi to k, and now you sum the rank over this ui. Okay, so it's the notion of linearized Reed-Solomon code, and I told you before that the Gabidulin code were used for network coding, and linearized Reed-Solomon codes are also application in the concrete life, and it's used for what we call the multi-shot network coding. So I don't want to say much about this because I don't know that much actually, but it's not only a beautiful mathematical construction, it also has applications. Yeah. So now I would like to, maybe I keep this on the blackboard for a moment, and I would like to give you, to reinterpret this construction in a more geometrical setting, spirit. So for this I need to explain more things on OA polynomials. So let me first introduce this notation. R is a dimension of k over f. So it's the order of phi. And I consider this ring, which is a ring of Laurent OA polynomial, I don't know, so it's an OA polynomial in x and x minus 1. And because phi is bijective, it's not a problem, because we have this commutation relation, which is x minus 1 times a is phi minus 1 of a times x minus 1. So this ring has two important subrings. The first one is f to the x to the r and x to the minus r, Laurent polynomials in f in the variable x to the r, and it's actually the center of A. So will play a quite important role. You can check this, it's not difficult. And in between, maybe I will write this again on the blackboard. So here you have A, which is k of x. Here you have the center. And in between you have C, which is k of x to the r and to the minus r. So this is the center of A, and C is a maximal commutative subalgebra. Okay? And what you can do is you can extend scalar to C, from Z to C. And in that case, on the here, well, this way. So you have the tensor product. And since this C over Z is a Galois covering, because it just obtained by extending scalar from K to F, which is a Galois extension, then C tensor C over Z is just split as a product of copies of C, of R copies of C, C to the R. And here you have C tensor A, and it turns out that C tensor A are also a very interesting interpretation. We have this isomorphism. C tensor A is isomorphic to the algebra of C linear transformation of A. So the mapping is the following. Okay, so C tensor A maps to the C acts by multiplication on the left, and A acts by multiplication on the right. And the important point is that A is a C module, of course, but which is free of rank R. The basis, for instance, is 1x, x squared, x to the cube, and x to the r minus 1. And so this is just a matrix algebra over C of dimension with R rows and R columns. So A is some array polynomials, but when we extend scalar from Z to C, then we get a matrix algebra. And if you know algebraic geometry, you might know that this is a definition, almost a definition of Azumaya algebra. So Azumaya algebra is an algebra which becomes isomorphic to a matrix algebra after an étale extension. And here the extension C over Z is étale, because it comes from, as I said before, it's a Galois covering. It comes from the K. It's deduced by scalar extension from the extension K over F, which is Galois. So we have an Azumaya algebra, and when you have an Azumaya algebra, you have a lot of interesting facts. So for instance, we have what we call the reduced trace, coming from the trace. So when you have a matrix algebra, you have the trace, a determinant, and so on. And this descends to A. So you have a reduced trace map, which comes from A to Z, to Z, I don't know, which is given by this explicit formula. It's not so important if you can see the formula. Just to say you that it's explicit. And in the same way, you have the reduced norm, and the reduced norm corresponding to the determinant. And also you have an explicit formula only for polynomials of degree 1. Otherwise, it's much more complicated, but anyway. I won't use them. And so now I just rephrase this. So it's a commutative diagram I had before. And now I can just make a picture instead of diagrams. So I draw the spectrum of the center, spectrum of Z, just a straight line. It's A1 with 1 point removed. I have a covering of spec Z by spec C, which is a straight line, but defined over K, not over F. I have another copy of spec C here, and now I have the tensor product. So the fiber product is disjoint of R copies of spec C, so R equals 2 in my drawing. And so above 1 point, I have 2 points, and I can consider the vector space, the k vector space generated by these 2 points, which are drawn here. And when I let the point vary on the axis, I can just make the construction vary on the so the vector space move on the top, and what I get is a vector bundle. And this isomorphism, saying that C tensor by A over Z is equal to some matrix algebra, just says that C tensor A is the endomorphism of this vector bundle. And in fact, you can just let phi act on the endomorphism of this vector bundle, and so A can be recovered as the endomorphism of this vector bundle stable by phi. So I don't know how to draw spec A because A is non-commutative, and I'm not really I don't really know how to draw the spectrum of a non-commutative algebra, so I just don't do it, but doing the endomorphism of the vector bundle.
Can you say again what the vector bundle with the fibers? It's a vector bundle over C?
It's a vector bundle over C whose fiber is just so it's a trivial vector bundle over C of dimension R. And if I have some point Z on spec Z, I can try to figure out what is the fiber of A over Z, which is by definition this quotient. And by the general theory of Azumaya algebra, you know that it's a simple central algebra over Z. The point is that this vector bundle does not descend to C. And so it's a simple central algebra, which is in general not endomorphism algebra, just a simple central algebra. But for instance, if you are working over a finite field, all simple central algebra are matrix algebra. And in fact, we have a characterization. This simple central algebra is split if and only if Z is a norm in this extension. And in that case, so in that case, it means that if it's split, it's an endomorphism of some vector space above Z. And so I'm just drawing this vector space here. But you have to be very careful. The vector bundle does not descend on Z. So just the fiber here. And so in that case, this isomorphism, I mean the splitting of this isomorphism is given by this map evaluation of A phi I've defined before. So this evaluation of mapping f of x to f of A phi realize this splitting, and so it's a way to see that the fiber of A over Z acting on this vector space. And so what is linearized with Solomon code? It just, you have some element of A, and each time you have a point on spec Z, you can evaluate it. You have this evaluation map. This evaluation map gives you an endomorphism of K, and K can be seen as something lying above Z. So what you have to maybe to retain is that the Gabidulin code actually is something lying over, living over a point, the point 1. We have a vector bundle of dimension, a vector space of dimension 1 over a point, and the linearized Gabidulin code is the same situation, but we just evaluate at not only at 1 but at many other points. Okay, so it's a drawing. And you can wonder if we can do this in a more general situation instead of having a covering of P1 by P1 or A1 with 1 point removed by A1 with 1 point removed. try to do this in a more geometric situation where we have a curve on the bottom and another covering, which is a cyclic Galois covering. But it's actually a work in progress. I won't say so much about this, but it's something which would be linearized geometric codes or something like this. So it's a very, very early stage. So I just started this work with Amaury Durand, who will be a PhD student of mine next year. Okay. So in the 5-10 minutes I will just want to speak about duality. Maybe I won't finish what I want to say about this, but I think it's important. So the starting point is this theorem. If you have a Reed-Solomon code, which was defined, I remember, by this evaluation formula in the very classical setting, then we can define the dual of this code. So by definition, the dual is the orthogonal for the usual standard product of k to the n, on k to the n, natural pairing. And the dual of this code is the image of, it can be described as the image of another mapping, given in terms of residues. This is quite interesting because the dual of a code in general is defined is an intersection of hyperplane, but here it is described as the image of something else. The proof of this is not difficult. It's just a residue formula and an argument dimension. But there is an interesting corollary is that using this description, you can prove that the dual of Reed-Solomon codes actually also meets the Singleton Bound. So not only the Reed-Solomon codes are MDS, but the dual of them are also MDS. And what I want to do is try to generalize this result to a linearized Reed-Solomon code. So if I have the dual of a linearized Reed-Solomon code, which is this code I defined before, I want to have a description of the image of the dual. So there are some difficulties. So of course, we are now looking for the image of something coming from defined in terms of array polynomials. The problem is that we don't know what is the residue for array polynomials. We have to define this. And the second point is that now we no longer have something with image in k to the n, but in this endomorphism of k to the m, and so we have to define a pairing on this space. So there are 2 points to do, so 2 things to do. So I'm starting with a residue. For this, I need to figure out what is a good Taylor expansion for array polynomials, if they exist. So Taylor expansion is nothing but trying to evaluate array polynomials on some thickening. And so I say array polynomials are endomorphism of some vector models. The point is that on the left-hand side, of course, this is a trivial vector model. You can just consider the image over a thickening of a point, and then you get a thickening of the vector models, no problem. But on the right side, it's not so clear what you get. And here comes the theorem saying that if you have a closed point in spec Z, that is an irreducible polynomial in Z, then there is an isomorphism between this projective limit corresponding to the function of the thickening and a ring of power series ring over the fiber, the special fiber. And okay, maps N to H. And from this we can define a residue of array polynomials. So first of all, I need to define the fraction field of A, because if I want a residue, I want a fraction. So it's defined as A tensor frac Z, the quotient. So okay, I skip this. And now I have the residue map, so I'm considering N a reducible polynomial in Z. If I have an array polynomial, I can just map it to it, consider this Taylor expansion. And I can use the previous theorem to see the Taylor expansion as a real, as a concrete series in H. And then I can just consider the fraction field on the left. Then it's, since N maps to H, it maps to this projective limit where N is inverted. And on the right-hand side, it maps to a Lorentz series with coefficient in A over NA. And now I can consider the coefficient in h minus 1, as for the usual residues. And I call this composite the residue at n. And I can define the residue at A as the residue at this polynomial, which is the point z over which A is defined, and I evaluate at A is this. And this way I get an endomorphism of K. Okay. Yeah, just a minute. So just one slide. And now I can define a pairing of the endomorphism of A. For this, I need to proceed by steps. Okay, so I first define a pairing on K, which is a usual pairing given by the trace. Sorry. Then I can define a pairing over the endomorphism of K by taking this usual formula, the trace of the adjoint of U composed with V. And then I have a pairing on the mapping, which is the sum of the trace. Okay. And this can actually be pulled back on array polynomials. So the pairing is defined by this formula. You see that the trace and the adjoint, and it turns out that the trace and the adjoint have some analogs on array polynomials. So for the trace, we have seen that we have the reduced trace here, and it's easy to prove that the reduced trace makes this diagram commute. So it's when you evaluate. So after evaluation, the reduced trace becomes a trace. And Oe himself defined a pairing on array polynomials, which is defined by this formula. Define adjunction on array polynomial defined by this formula. Sum of ai xi is the adjoint of this is the sum of x minus y ai. And after evaluation, this becomes a natural pairing on. This adjunction becomes the adjunction I defined before on the endomorphism of K. And using this, you see that the pairing of evaluation of G and evaluation of F at this point is actually the reduced trace of G star F evaluated at some point. And you can, yes, I'm finished. And you have the same thing for the residue. The pairing of the residue and evaluation is the residue of the reduced trace of something. And using this, you can finally prove this theorem, which is that the dual of the linearized with Solomon code is the image of this, of a code like this, where you have the residue at AI inverse of something like this. And the corollary of this is that the dual of linearized with Solomon code meets the Singleton Bound as well, as for read Solomon codes. And I'm done.